Pre-calculus students, these are your 9.5 notes, the binomial theorem. We're going to take a look at some work from our good friend Pascal from many years ago. I should caution you as you walk through these notes today, there will be times when I will skip ahead and not show you every single step of my work. I think it'll be explanatory when you look at it, but there may be moments when you need to pause so that you can catch up in writing some things down. So let's get started. So what we're going to start with today is a look at something called NCR. So in the expansion of the binomial x plus y to the nth power, the coefficient of x to the n minus r, y to the r is found by using this NCR formula. I use some factorials. So NCR means n factorial over n minus r factorial times r factorial, and I note here that you can see two different ways you can write NCR. Sometimes it's used with the c, sometimes you just have these parentheses with the n over the r. So we'll take a look at how this works. So first of all, 8c4, that's just simply another way of saying 8 factorial divided by 8 minus 4 factorial times 4 factorial. Now, as you know, 8 minus 4 is in fact 4, so really what we have here is 8 factorial over 4 factorial, 4 factorial. And perhaps instead of writing 8 factorial again, though, I might be wise to do this. 8 times 7 times 6 times 5 times 4 factorial divided by 4 factorial, 4 factorial. And one of those 4 factorials is gone. Now, we could do some simplification, and I would look at it this way. I know that 8 times 7 times 6 times 5 is my numerator. I'm doing this by hand, so I'm not going to stoop to the level of using a calculator to do this work, but I do know this. 8, we could cancel with a 4 times 2, and then I have 6 divided by 3, so I could just make that a 2 up there. So what I'm left with is 7 times 5 times 2, which is 70. All right, so number 2, let's do the same thing. We're using the alternate notation here, but this is the same as saying 10c6. And so what we would do here is the numerator would be 10 factorial. The denominator is 10 minus 6 factorial times 6 factorial. Would look something like that. And 7 times 10 is 70 times 3, 210. All right, why don't you guys do this? Pause the video, do the next 3 on your own, and then compare your answers to. All right, welcome back, folks. You can see my work on 3, 4, and 5. Quick reminder, 0 factorial, you see it a couple places here, but 0 factorial is actually equal to 1. So don't start thinking, oh, that's undefined. It's not. It's definitely defined. It is 1. Hey, one more thing I want to show you too, those of you into the technology. We have a couple ways to attack NCR notation. One of them you can get from, if you just hit alpha and then F2, you will see down at the bottom option number 8 is NCR. And if we were to look at example 4, which is 7C5, we could just punch it in just like it would look if we used the other notation, and we'd get confirmation that 7C5 is in fact 21. Now, those of you that don't have the Color Plus calculator, the Plus C Silver Edition, like you see on my screen, you have another way of getting there. If you hit the Math button, and then you head over to the 4th option here, prob. There, you'll probably have the right things down here. You also notice you have a factorial. You have another one called NPR, which we'll get to another day. All right, next we're going to take a look at Pascal's triangle. You can see it over here on the left. I have a nice poster in my room if you wanted to take a look at other patterns that exist. But what I want to do is start filling out Pascal's triangle. The number up top here is a 1. And essentially what we do is every spot comes from adding the 2 spots above it. So like this place right here, I have a 1. I don't have anything over here, so it's just simply a 1. Same situation here. Then it starts to change. So I have 1, and then those 2 add up to 2. So 1, 2, 1, and then 1, 3, 3, 1, and so. You can see the completed Pascal's triangle now, and really that's not the right way to say that. That's not completed because this triangle is infinitely tall. You could go as many rows as you would like. So this continues. The pattern continues infinitely. All right, now one cool thing is that we could actually use Pascal's triangle to do evaluation of NCR notation. So what we have to think about, though, we have a couple of little weird things to consider. First of all, you have to consider this right here to be the 0th row, and then by the same token, if we think of these as columns, this is the 0th column. And so what's going on here is this would be the 0 column, this would be the 0 row. So when we see 6C3, that means I need to go to row 6. Well, that's 0. There's 1, 2, 3, 4, 5, 6. By the way, little hint, second number is 6. That's row 6. And then we need to go to the third column. Now the weird thing is it starts with 0. So there's 0, there's 1, there's 2, there's 3. So we'd be talking about that number right there. It's 20. You could do the same thing if you wanted to check that. You could plug it in the calculator, or you could just evaluate it by hand. But we can use Pascal's triangle to evaluate. All right, so number 7, we do the same thing. We find the row that's row 5. That's right here, and then we go to the fourth column, which remember that's 0. Then 1, 2, 3, and 4, and we would have this number right there, and it is a 5. Now we'll take a look at the reason we actually, discuss or are concerned with Pascal's triangle for binomial expansion. Let me show you how this works. So we see a binomial like x plus y raised to the 6th power. What I need to do is think about the coefficients from row 6. That's the row that starts with a 1. All of them start with a 1, but then it goes 6. And then after that, and you can just look back at the triangle to get these numbers. Sometimes you might have to do a little work to get there, but it's 1, 6, 15, 20, 15, 6, and 1. So what I'm going to do is use these 7 coefficients, so starting with a 1. Then I take the first term, which in this case is just simply an x, and it goes to the highest degree, which in this case is 6. And then our y term is just to the 0 power. Then plus, and we use the next coefficient, which is of course a 6. And then our x value, what we do is we decrease the power by 1. Then we go to the second term, which is y, and we increase the power by 1. And we continue with this. So the next coefficient is 15. And then we take x and we drop the power by 1. Y, we increase the power. We continue on, 20, and this time it'll be x to the 3rd and y to the 3rd. So again, the first term, the powers are descending. The second term, the powers are ascending. And continuing on until what eventually happens is x is to the 0 power, like you see here. Now, the only thing I have left to do is just some simplification. We don't like things like a y to the 0. So I'm just going to rewrite this x to the 6th plus 6 x to the 5th y plus 15 x to the 4th y squared. There's not a ton of simplification to do on this one. Just a little bit. Get rid of those 0 and 1 exponents. We don't really need them. And your answer looks like that. So kind of a long answer, a long expression, but I don't think anybody would prefer to actually multiply x plus y 6 times to get there. It's a much simpler pathway. All right, let's look at number 9. Same approach. This time it's 4th degree, so we're going to use the row that starts with a 1 and then a 4. The numbers after that are a 6 and then another 4 and then a 1. So we're going to set it up like this. We're going to have 1 times the first term to the highest power, which is 4, times the second term, which in this case is negative 2, to the 0 power. Then we go to the next coefficient, reduce the power of y, increase the power of negative 2. And now you can see the rest of the work on number 9. Essentially, just continue until your first term gets to the 0 power and the last term gets to the highest power, and then simplify. Notice the alternating signs, but this is my expression. That's y minus 2 to the 4th. All right, let's do this again. This time we have a 5th degree binomial. And so again, we have to look back at Pascal's triangle, and the row that we would use has the coefficients of 1, 5, 10, 10, 5, and 1. And we'll set up our expanded binomial. I've now expanded the binomial, so my next step is to simplify. So I'm going to look at this one term at a time. 2x quantity to the 5th is 2 to the 5th, which would be 32x to the 5. Then in the next term we have 5 times 16 times negative 3, which would give us negative 240. And you can see the final result here. All right, number 11, pause the video and try doing that one on your own. It's not horribly complicated, but see how those squares impact things. All right, welcome back. You can see my work. It's a lot of terms, 7 of them to be precise, which makes sense since it is in fact a 6th degree polynomial, or binomial I should say. But then when you look down below, notice that all the powers are much larger than 6. Something to keep in mind. So powers inside the groupings will have an impact on your results, but not an impact on the process. All right, now we're going to use this a little bit different way. We're going to use our NCR situation so that we can find the nth term of an expansion. Now, I'm not going to actually do x plus y to the 9th all the way through. What I'm going to do is this. When we think about the 6th term of that sequence, x plus y to the 9th, what we'd be talking about is a term that has x to the 4th power and y to the 5th at the end. The key here, this 5 is 1 less than the 6 because it starts at 0 and increases 1 step each time. So the 6th term is x to the 4th, y to the 5th. Now we can get this, the coefficient, from doing 9c5. Now you guys can do that by hand or you can punch it in the calculator, but either way you should get 126 for 9c5. And so then we would just plug it in and say, okay, so I've got 126 times my first term x raised to the 4th power, and my second term y is raised to the 5th power. Okay, so now let's look at 13 where we have some coefficients in the mix that'll complicate things slightly. Our n equals 5 term, we're going to use 5c4 in this particular case. Essentially, you're using the exponent 5 goes right here, where we do n minus 1 for the second part of our NCR. So 5c4 is equal to 5. And so then I'm going to have 5 times, now my first term, remember it's 5a, and the power starts at 5 and then descends 1 step each time. So it's basically just 5a to the 1st, where our second term is b, and that would be increasing by 1 each time. So if we're on step 5, it would be up to the 4th power. So what we're left with is 25 times a times b to the 4th. One more slightly different way we can look at this would be like these last two. We're going to find the coefficient of the term given. So this is x to the 4th, y to the 8th. Now notice inside the groupings though, so I'm going to actually think of it as this term. This is x squared squared and y squared to the 4th. So what we're going to do here is 6c4. Again, coming from that second value, 6c4 is just simply 15. And so we would have 15 times x squared to the 2nd and y squared to the 4th. Now this just asks for the coefficient, so our answer is 15. Why don't you try number 15 on your own? All right, you can see my work on number 15. The coefficient there was all they're actually asking for would be 7,920. Folks, I know that's a lot on your notes today. Come to class ready to work and ready to keep me busy by asking me lots of questions. Have a fabulous day.